Another important application of Bernoulli's principle exists in a concept known as dynamic lift. So let's examine two instances in which dynamic lift is evident. So let's begin with the wing of an airplane. Let's suppose that we have an airplane that is traveling in this horizontal direction along the x-axis, and this black region is the side view of the wing of our airplane. Now notice, because the airplane and the wing are traveling in this direction, in the negative direction along the x-axis, the air molecules are rushing in the opposite direction. So if we take the reference frame of the wing of the airplane, then that means we're going to have streamlines of air that will rush in this direction, in the positive direction along the x-axis, as shown by these blue regions. So each blue pathway is simply the streamline of our air molecules. Now, because our airplane wing is at an angle with respect to the x-axis, with respect to the direction of motion, notice what happened to our streamlines of air on the top portion of our wing. Notice that these streamlines collect together. They bunch up at the top portion, and they are more separated on our bottom portion. In fact, because the area between any two streamlines on the top portion of our wing is smaller than the area between any two streamlines on the bottom portion, we know from the equation of continuity, because the area is smaller here, the velocity must be higher. So the velocity of the streamlines on the top portion of the wing is higher than the velocity on the bottom portion of the wing. And we know from Bernoulli's principle, where the velocity is higher, the pressure is lower. So because the velocity of the air on top of the wing is higher, the pressure must be lower. And because on the bottom portion of the wing, the area is higher, the velocity is smaller, and so the pressure is higher on the bottom portion of the wing. So that means there is a higher pressure that's pushing on our wing from the bottom than from the top. And that change in pressure, that pressure difference between the top and bottom portion of the wing, will create a net force that will point upward along the y-axis. And this net force is known as dynamic lift. So dynamic lift is simply a force that acts on our object, in this case the wing of an airplane, that lifts our wing up and therefore lifts our plane and allows the plane to continue flying in the air. So once again, the wing of a plane is at a slight angle, causing the air streamlines on the top portion of the plane wing to bunch together. The area between two streamlines is therefore reduced. So the area between any two streamlines on the top portion of the wing is reduced. And from the continuity equation, because the area is reduced, the volume must increase. So the reduction in area on the top face of the wing causes the velocity of the streamlines of air to increase. And this increase in velocity, the fact that there is a higher velocity of air on the top portion of the wing than on the bottom, there will be a lower pressure on the top than on the bottom. And because the pressure on the bottom will be higher, there will be a difference in pressure between the top and bottom portion of the wing, and this will in turn create our dynamic lift force that will lift our wing up into the air. So our force dynamic lift is simply the change in pressure multiplied by the surface area of that region on which the pressure is acting on. Now let's talk about baseballs. So how exactly is it that baseball players are able to curve the ball? So when you throw that ball, the baseball curves as it travels along a horizontal axis. So how can a baseball thrown with a horizontal velocity follow a curved horizontal path? So let's examine the following baseball, and let's suppose the baseball is thrown in this general direction along the x-axis. So as the baseball is thrown and it travels in this direction, the air molecules are traveling in the opposite direction. So if we take the reference frame of the baseball, the streamlines of air are traveling in the negative direction along the x-axis as shown in blue. Now, when we actually throw the baseball, we put a spin on that baseball. Our baseball is not only translating, it's not only moving along the horizontal axis, it's also rotating as it's moving. So let's say the rotation is in the counterclockwise direction. So look what happens as the ball rotates. At the top portion of the baseball, the ball rotates in the same direction as the movement of air molecules. So the velocity of the air molecules on the top portion of the ball increases. At the same time, on the bottom portion of our baseball, the ball rotates in the opposite direction of the air movement. So the velocity of the air on the bottom decreases. So once again, according to Bernoulli's principle, because we have a lower velocity on the bottom, we have a higher pressure. And because we have a higher velocity on the bottom, on the top portion of the ball, we have a lower pressure. And this difference in pressure between the top and bottom portion of the baseball will create a net force that will act along the vertical axis and will point upward. And this force is known as, once again, dynamic lift. And it will allow the baseball to curve as it travels along a horizontal axis. And this is exactly what creates the curve we know of. So once again, the reason that airplanes are able to fly and remain in the air as they travel along the horizontal axis, and the reason that baseball or tennis balls are able to curve, is because of a concept known as dynamic lift, which is explained using Bernoulli's principle.